Welcome to our module on robotics and perception, where we explore how robots interact with their environment. We'll delve into understanding how robots move, sense their surroundings, and navigate effectively in space. Let's begin by examining key kinematic representations, which are crucial for defining robot structure and movement. These representations help us describe a robot's pose and the complex relationships between its various links. First, we have the homogeneous matrix, a powerful tool for combining various transformations in robotics. Here, matrix T combines the rotation matrix R, position vector P, a zero-vector transpose, and 1 for spatial representation. The symbol T here stands for the homogeneous transformation matrix, representing a complete pose in space. R denotes the rotation matrix, which defines the orientation of the robot's coordinate frame. P is the position vector, indicating the translation or location of the robot's coordinate frame. The term zero-vector transpose, or zero-vector T, ensures the matrix maintains its homogeneous structure. This matrix is used to describe the position and orientation of a robot's end effector relative to a reference frame. Crucially, it combines both rotation and translation components into a single, elegant matrix representation. Next, let's explore Dennevit-Hartenberg, or DH parameters, another fundamental concept in robot kinematics. The overall transformation matrix T is the product of individual transformation matrices, T sub I, for each joint. Here, T represents the overall transformation matrix, describing the robot's complete configuration. Each T sub I is the transformation matrix for joint I, defining the relative pose between adjacent links. The parameter, a sub I, denotes the link length, representing the distance between joint axes. Alpha sub I is the link twist, describing the angle between successive joint axes in the robot. D sub I is the link offset, which is the distance along the joint axis between common normals. And theta sub I represents the joint angle, defining the rotation about the specific joint axis. DH parameters provide a standard convention to define coordinate frames for each robot link. This method significantly simplifies the kinematic modeling of complex serial manipulators, making them easier to analyze. Now, let's shift our focus to key dynamic formulations, which govern robot motion and the forces involved. These equations help us understand how robots move under various forces and torques that act upon them. Our first dynamic formulation is the Lagrangian equation, a powerful energy-based approach to robot dynamics. The Lagrangian, denoted by script L, is simply the kinetic energy T minus the potential energy V of the robot system. Here, script L represents the Lagrangian itself, a scalar function summarizing the system's dynamics. T stands for the kinetic energy of the robot system, representing its energy due to motion. And V represents the potential energy of the robot system, related to its position in a force field. This equation forms the crucial basis for deriving a robot's equations of motion using energy principles. Essentially, it's the fundamental difference between the total kinetic and potential energy of the system. Next, we have the fundamental equations of motion, describing how torques create robot movement. This equation describes robot motion, linking the mass matrix M, Coriolis C, and gravity G to the applied joint torques tau. M of Q is the mass matrix, representing the robot's inertia, dependent on its joint positions Q. C of Q and Q dot is the Coriolis matrix, accounting for velocity-dependent forces on the robot. G of Q is the gravity vector, representing gravitational forces acting on the robot links. Tau is the torque vector, which represents the forces or torques applied at the robot's joints. Here, Q represents joint positions, Q dot signifies joint velocities, and Q double dot denotes joint accelerations. This comprehensive equation describes the intricate relationship between joint torques and the resulting robot motion. It is absolutely fundamental for designing effective robot control systems and performing accurate simulations. Finally, let's explore the core elements of simultaneous localization and mapping, or SLM. SLM is all about how robots build maps of their environment while simultaneously knowing their own place within it. Localization is a key component, focusing on where the robot is in its surroundings. It involves precisely determining the robot's current position and orientation within an existing map. Mapping is the other critical element, creating a representation of the environment itself. This involves building an accurate and consistent representation of the robot's surroundings. The importance of SLM cannot be overstated for truly autonomous systems. It is essential for autonomous navigation, especially in unknown or dynamic and changing environments. Today, we'll discuss overcoming the significant obstacles and challenges encountered in simultaneous localization and mapping, or SLM. These are the key challenges that researchers and engineers face when implementing SLM for various robotic applications. First, data association involves correctly matching observed features from sensors with the existing features already on our map. Next, loop closure is crucial for recognizing when a robot revisits a known location to correct accumulated map errors. Scalability addresses the challenge of efficiently managing very large maps and complex, dynamic environments. Finally, sensor fusion focuses on combining data from various sensors to achieve more robust and accurate localization and mapping. Let's explore the different types of SLM algorithms, each offering unique approaches to mapping and localization. These algorithms represent various methodologies and techniques used to simultaneously build maps and localize robots. First, we have EKF-SLM, which utilizes the extended Kalman filter for probabilistic estimation. It estimates robot pose and map features probabilistically, but can be computationally intensive and less accurate in large environments. Next, we'll examine particle filter SLM, a robust method for handling uncertainty. This method uses a set of particles to represent possible robot and map states, handling nonlinearities better than EKF. Then, there's graph-based SLM, a popular choice for large-scale applications. It represents trajectories and maps as a graph, optimizing nodes and edges, which is great for large environments and loop closures. Now, let's dive into the core path planning algorithms that guide robots from a starting point to their goal. These algorithms are essential for enabling autonomous robots to navigate safely and efficiently through their environment. First, Dijkstra's algorithm finds the shortest path in a weighted graph, guaranteeing optimality. It systematically explores all possible paths to ensure it identifies the absolute shortest route available. Next, we have the asterisk algorithm, an improvement over Dijkstra's. It significantly improves Dijkstra's efficiency by using heuristics to intelligently guide the search towards the goal. Then, the rapidly exploring random tree, or RRT, is excellent for high-dimensional spaces. This sampling-based algorithm efficiently explores complex, high-dimensional spaces to find feasible paths quickly. Another approach is the potential field method, which uses attractive and repulsive forces. It guides movement by creating virtual attractive forces towards the goal and repulsive forces from obstacles. Finally, trajectory optimization refines the entire path for optimal performance. This method optimizes the entire path to ensure it is smooth, efficient, and dynamically feasible for the robot. Let's outline the general flow of path planning, which typically involves a series of sequential steps. The first step is for the robot to sense its environment, gathering crucial data about its surroundings. Next, the robot needs to localize itself within that environment, determining its precise position and orientation. Following localization, a map is created or updated, building or refining the robot's understanding of the space. Once the map is ready, the system can then plan the path, calculating the optimal route to the destination. Finally, the robot will execute the motion, following the planned path to reach its intended goal. All right, let's wrap up our discussion with a concise summary of the key concepts we've explored today. Here are the most important takeaways you should remember from our session on robotics and perception. Remember, kinematics focuses on robot motion, while dynamics delves into the forces and torques causing that motion. SLAM is crucial for robots, allowing them to build a map and pinpoint their location simultaneously in new environments. Path planning ensures robots navigate safely and efficiently from a starting point to a goal, avoiding all obstacles. We learned that homogeneous matrices and Dennevit-Hartenberg parameters are fundamental tools for robot kinematics. For robot dynamics, the Lagrangian and Newton-Euler formulations are absolutely central to understanding motion. SLAM, while powerful, does face challenges, particularly with data association and achieving effective loop closure. Finally, algorithms like a star, and RRT are essential for robust and autonomous robot path planning.